Hello everybody. Yeah, we have not so many students, but so we continue our consideration of plane curves. And I finished last lecture with the following formula. We wanted to compute this second derivative, and it was equal to the following thing. Minus. Now I'll change a little bit. So this formula is not precisely same as it was written before. Now I'll explain where is difference. Prime of t. So what is difference with respect to the very last formula from the former lecture? The difference is here. So it was written as follows. This was written in the last line from the former lecture. So you see, the very last formula from the former lecture, the difference, small difference, was here. It was written like that. So now what I am doing, I replace this derivative with respect to the arc length parameter. We know that it is related by the following formula. So you see, instead of derivative with respect to s, we use derivative with respect to t, but one extra modulo of r prime, because derivative with respect to s is equal to derivative with respect to t divided by the, okay, I'll write like that, ds over dt. And ds over dt is nothing else but this r prime in modulus. That is what was used to write down this formula. Okay, so now we can continue this formula by using the representation for ds over dt. That is precisely modulo of r prime of t, according to the theorem about arc length. So derivative of the arc length parameter is equal to that one. So if we use it, then I will write it shortly as s prime of t. So what we obtain, right, with common denominator s prime of t cube, right? And then here s prime of t times r double prime of t minus, that is s prime, so s double prime of t times r prime of t vector. Now remember main definition. So R of t is our curve. And we can write it in coordinates like that. Remember, we consider plane curves, so only two coordinates. X coordinate and y coordinate. And vectors I and j are x-axis, y-axis, and that is I, that is j. Unit vectors, so that's 1, 1. Then, what is r prime? R prime of t is x prime. Okay, I'll write shorter without t, like that. I'll omit t here, otherwise it will be very huge. So, also second derivative, double prime of t equals to x double prime I plus y double prime j. Also, what is s prime? S prime of t is the length of r prime of t. R prime is written here, so that is square root of x prime squared plus y prime squared. Okay, then what is s double prime? S double prime of t. Let us compute as a using chain rule. So firstly, derivative of square root is 1 over 2 square roots, the same expression. Then I should multiply to derivative of the expression under square root. And what is it? So 2 times x prime times x double prime plus 2 times y prime times y double prime. That is okay. So now let us substitute all those formulas into our second derivative of r with respect to s twice. So what is it? And it is more convenient to multiply by s prime of t both numerator and denominator. So yeah. I will not write. Okay, maybe I'll spend time to write it down. S prime of t squared r double prime minus s prime of t s double prime of t r prime of t over s prime of t power 4. So I multiplied both numerator and denominator by s prime. Why? Because it is essentially more convenient to write square of s prime. You see, here we have square root, right? And then we forget about this square root. Also, I forget about those 2 multiplies 2, cancel them. So what we obtain? S prime squared, it's here, x prime squared plus y prime squared, that is s prime squared. Then r double prime is here, x double prime I plus y double prime j, then minus s prime times s double prime. Look, this square root is nothing else but s prime. So if I multiply this expression by s prime, then square root is cancelled. So what remains? That one. So x prime x double prime plus y prime y double prime. Yeah, this expression is written. Then r prime, that is x prime I plus y prime j. That is everything with numerator, and denominator is s prime power 4. It means this expression squared. X prime squared plus y prime squared squared. Yeah. The curves you write. Curve gamma is given by this parametric equation. Curve gamma is given by this parametric equation. R of t is parametric equation for our curve gamma. Okay? So, now let us open brackets and write down what we obtain. So, rather huge expressions, coefficients in I and then in j. So, firstly, coefficient in I. X prime squared x double prime plus y prime squared x double prime, that is here, minus what we have here, x prime squared x double prime and x prime y prime y double prime. That is in I, coefficient in I. Then coefficient in j. Coefficient in j is, okay, x prime squared y double prime plus y prime squared y double prime minus x prime x double prime y prime and minus y prime squared y double prime j. Yeah, that is numerator. Denominator is the same. Okay, then look, cancel and cancel that one. So what are common multipliers, better to say? Look, y prime is a common multiplier here. What remains? Y prime x double prime minus x prime y double prime. And here, x prime y double prime minus x prime double x double prime y prime. Same. So look, but with minus sign. So let me write like that. Y prime x double prime minus x prime y double prime is a common multiplier for both. That is common multiplier for both. What do we have in brackets then? Here, y prime I, and over there, look, that is minus x prime j. Yeah. And divide by x prime squared plus y prime squared squared. And in fact, it is better to write like to change the order in both. Why? Because of the formula for the curvature. You will see later. So that is minus y prime I plus x prime j. Squared. Okay. That is, recall, that is what I started with, second derivative of r with respect to s twice. Now, remember what was our main task, main goal. The main goal was to find equation for the evolute. Evolute, it means I need to find coordinates of center of curvature. Center of curvature was written as r of s plus r times n. R radius of curvature, n is normal. Now, remember, it was in the definition of curvature, in fact. So, d2r over ds twice is equal to kappa times n. That was in definition of curvature and of the normal vector together. It was one of main formulas. And also, r is 1 over kappa. Then I can substitute, so 1 over kappa is here, right? If I put kappa to the left-hand side. And 1 over kappa is just r. So n is r times that one. So I can rewrite it as r squared times d2r over ds twice. Okay. So you see now everything is obtained, in fact. Also, I need to recall what is r squared. So r squared is 1 over kappa squared, and yeah, that is why this expression appears. So you see precisely x prime y double prime minus y prime x double prime squared, and s prime cube, so s prime power 6 here. S prime cube for curvature, so squared of curvature power 6 appears. Yeah, and also remember, for kappa we had that divided by s prime cube, modulo of that, right? But of course, when we take square, we may forget about modulus, right? Okay, so now everything is ready. Look, so what is it? So now rho, I may forget about argument, is r plus, okay, substitute r squared, s prime power 6 over x prime y double prime minus y prime x double prime squared times d2r over ds twice, written here, x prime y double prime minus y prime x double prime minus y prime I plus x prime j over, that is s prime power 4. power 4. Okay, so we can cancel common multipliers, right? And what remains? Plus s prime squared minus y prime I plus x prime j over x prime y double prime minus y prime x double prime. Finally, we can write now equations, parametric equations of the evolute. We obtained them. Let me write them. So evolute psi of t eta of t, maybe psi of t I plus eta of t j, that is rho of t now, right? And let me write in coordinate. Psi of t equals to r first coordinate x of t plus, okay, maybe I forget about t, sorry. I forget about t, otherwise it's huge. Yeah, not plus, minus. We have minus here. Minus y prime times x prime squared plus y prime squared over x prime y double prime minus y prime x double prime. That is for the first coordinate, and for the second coordinate, eta equals to y plus x prime squared plus y prime squared over x prime y double prime minus y prime x double prime. Yeah, that's it. So our goal is achieved. And in fact, that is the end of chapter 1. So we completed theory of curves. Both section and chapter are over. So chapter 2, it contains two different topics, in fact. So line integrals and measure. So section 1 is devoted to integral along a curve. Or in Russian tradition, it is called curvilinear integral of the first kind. Also, it can be, sometimes it is called as line integral of a scalar field. These are same notions. under different names. By the way, I recommend there is a book in our library, so you can use it for this topic. I mean, for line integrals, it's very nice. Friedman, Auner Friedman. Yeah. Friedman is good with this topic. Also, by the way, bounded variation is also considered there. Of course, of course. Every textbook, oh, no. Most textbooks have no solutions for exercises. I see. Yeah, that is a book without examples. You are right. You are right. Here you are right. But concerning line integrals, I think in your lecture notes there are examples with solutions, how to compute line integrals. I don't remember. I think in your textbook it's line integral of a scalar field, like in Zorich, most probably. Yeah. Okay. So definition. Let gamma, let's say r of t, be a rectifiable curve in R3 or R2, doesn't matter. Rectifiable. Something wrong with rectifiable. Okay. In R3 or R2, and f be a bounded function on gamma. Integral sum for a partition P T naught less on less Tn equals to B is the sum, let's say, S of F P and also tau I, which is equal to the following expression: sum I from n to from I from 1 to n, f of tau I, r of tau I times Li, where tau I belongs to the interval ti minus 1 ti, and Li is the length of the arc r of t for t between ti minus 1 and ti. Okay, that is the definition of the integral sum. So now we can define the integral, the line integral along a curve. So it's continuation of the definition if for arbitrary epsilon greater than 0, there exists delta greater than 0 such that for any partition P with mesh maximum of delta Ti less than delta, and for any choice of tau I in Ti minus 1 without. So I in Ti minus 1 Ti, the difference between our integral sum and a number I less than epsilon, then I is called an integral not n, the integral of f along the line, the curve gamma, and notation is I equals to integral of gamma f of x, y, z ds for 3 variables and for 2 variables like that. So you see, the function f depends on x, y, z, I mean variables in R3 or R2, right? Because our curve in some way in R3 or R2. And you see the definition looks like a definition of the Riemann integral, right? Because we have integral sum and everything is very similar, right? But maybe it's a bad idea to use the same notation because you may mix. Let me change the letter. Let it be capital T here, because capital S is precisely like it was in Riemann integral, and you may mix with the same notation for Riemann integral. That is not a good idea. Yeah. So you see how, what is it? You see, we have a curve, right? And this curve, how it is obtained? We have an interval, right? And we may think about this curve as a trajectory. So it means that is t, right? T varies from A to B. And so here we have r of A, that is r of B. And we have a function which is given on our curve only. We don't suppose that the function is defined anywhere else, the curve, only along the curve. Then what we do? We consider arbitrary partition, right? That is our partition, T1, T2, and so on. So these are moments when our point is somewhere here, right? There is a corresponding partition on the curve, right? So here we have r of T1 and so on. Then what we do? We choose arbitrary points. For instance, here is τ2, right? τ2. So somewhere there it corresponds a point r of τ2. Then what we do? What is our integral sum? We take the value of our function at this chosen point, right? Multiply by the length of this piece and add all those sums. So what is the meaning? There is one very natural meaning, namely, so what is physical sense? Physical sense. Physical sense. If f is the linear density of gamma, then integral over gamma f of x, y, z ds is the mass of gamma. Why? Because look, we multiply density at a point. What is density at a point? You see, we think about this curve as a massive curve, right? But density varies. So some pieces of curve are heavier than other, right? It might be. Then what happens? We want to compute linear density. What is linear density? Roughly speaking, what we do? We divide mass of this piece onto the length, right? That is average density. And then what we do? We consider the limit as the length tends to 0. That is linear density at a point. So the function f is precisely this linear density at a point. The value of a function, right? Then what? What is it in the integral sum? We multiply density at a point times the length. So we replace the mass of this piece. We don't know it, right? But what we do? We multiply the value of density at one point onto the length. So obviously we approximate the mass of this piece, right? But when it is natural to expect that when lengths become smaller and smaller, right? So we have more and more intervals. So approximation is better and better. And finally, what we'll obtain? We'll obtain the mass of the curve. That is physical meaning of this integral. Okay, so let me correct two mistakes in English: curvilinear and rectifiable, right? Okay. Okay, let's continue. So the integral along a curve is defined, and now how to compute it. There is a theorem. Let me formulate it in a slightly different form, from easier, I would say, form than in Friedman. Slightly easier. So theorem 1. If gamma is a smooth curve in R3, then for any continuous function f on gamma, the integral over gamma f of x, y, z ds is exists and is equal to the integral f of x, y, z ds equals to integral from a to b f of x of t, y of t, z of t times r prime of t dt, where r of t is x of ti plus y of tj plus z of tk. So that is a parameterization. So that is how to compute the integral along a curve. And let me remark in practice what you should to remember. So that is why ds it is written here, because remember that we had a formula ds over dt equals to r prime of t, right? That is precisely is written here. So ds equals to r prime times ds. So you just substitute, right? So how to compute integral along a curve? Just to substitute everything. You see, r, x, y, z, you substitute, right? And also you substitute ds. That is good notation, right? Then you just substitute, if you know, of course, this formula, right? That is the only thing what you should remember. Okay, proof. So we know that, look, the integral in the right hand side is well defined. Why? Because you see, f is continuous, right? X, y, z is a continuous vector function. So as a composition of two continuous functions, that is continuous. as a composition of two continuous functions. And also we know that gamma is a smooth curve, hence this is continuous and is never zero, by the way, right? So that is also continuous. So we have a product of two continuous functions, and then we know the integral, Riemann integral, is defined for continuous functions. Then the integral, which is written in the right hand side, is equal to the limit as how this mesh I defined, mu of p or delta of p, I forget. In second semester, mu of p or delta of p, I don't remember now. Mu or delta? Delta? Okay, good. Tends to 0. That is mesh, right? That is mesh equals to delta of p mesh or diameter mesh of integral sums. And what are integral sums? Let me write them explicitly. If I have a partition like before, then integral sum will be f of x of tau I, y of tau I, z of tau I times r prime and tau I delta ti. That is the integral sum from Riemann integral, right? What it means in quantos: for arbitrary epsilon greater than 0, it means there exists delta greater than 0 such that for all partitions P with diameter less than delta, and for all points tau I in Ti minus 1 Ti, we have that the difference between, okay, let me denote the left hand side by integral I minus the sum f of x of tau I, y of tau I, z of tau I, r prime and tau I times delta Ti. Yeah, less than epsilon. That is the meaning of this limit. The meaning of this limit. Okay. Now, what we need to prove? We need to prove that this integral sum is sufficiently close to the integral sum T of f p tau I. So let us write down the difference. So consider the difference between the sum f of x of tau I, y of tau I, z of tau I, or maybe let me use now shorter notation, r of tau I. I'll not repeat it, right? Because that is precisely r of tau I. point times r prime of tau I delta ti minus our integral sum t of f p tau I. So what is it? That is, you see, f of r of tau I. You see, this term exists in both that one and the integral sum t, right? In both of them, we have this value of a function. Then the difference is in other terms. So what is it? R prime of tau I delta ti minus Li, right? Okay. So now I need to recall what is Li. Li is the length, right, of our piece. Which piece? I can compute it. According to the formula for the length, that is precisely integral from r prime of t dt, according to the formula for the length. Li is the length of this piece of our curve from r of ti minus 1 up to r of ti. So that is precisely this length. Then we can apply mean value theorem for integral. According to this mean value theorem, there exists a point, you see, that is a continuous function, right? So integral of continuous function is equal to the value of the function which we integrate at a point. Let me call it psi I, intermediate point, right? Times the length, and the length is precisely delta ti. So where psi I belongs to our interval ti minus 1 ti. So that is mean value theorem, right? So you see, practically what we can do now. Let me replace now. You see, modulo sum f of r of tau I times, and here I can write like that, r prime of tau I minus r prime at psi I times delta ti. Yeah. You see, I replace Li by this, right? And then delta ti is common multiplier also, right? What I used here. Now, what r prime, I forget. Now remember that modulo r prime of t is continuous. On AB, hence it is uniformly continuous by Cantor's theorem. Is uniformly continuous. On AB. Also, f is continuous on gamma, and gamma is a continuous image of a compact set, so it's compact. Gamma is compact. Continuous image of a compact set. So you see, those abstract things which were considered at the beginning of this semester, they work for many situations, in fact. Like here, you see, gamma is compact, f is continuous on a compact, hence f is bounded. On gamma, let's say modulo f of x, y, z less or equal capital M, right? That is a constant which is. And now I return to uniformly continuous. So what is uniformly continuous? If it is uniformly continuous, then what I know, for arbitrary epsilon greater than 0, there exists delta 1 greater than 0, such that for all, let's say, t prime, t double prime in AB, which are closer than delta 1, we have an equality modulo r prime of t prime minus modulo r prime at t double prime. This modulo of the difference is less than what? Epsilon over m times b minus a. That is uniform continuity is this. And now, look, I can estimate it. So, this works if delta of p less than minimum of delta and delta 1. That is an extra supposition. So if this is the case, then what happens? Look, the mesh is less than delta 1. It means that, remember, both points tau I and psi I, they belong to the interval ti minus 1 ti, right? The length of this interval is less than delta of p. Hence, it is less than delta 1. So, look, difference between those points in modulus is less than delta 1, right? Hence, we can apply this estimate for the difference between r primes. So, look, so this is less than epsilon over m times b minus a. This. Next, modulo f less than m, right? So, look, this less than m, next less than epsilon over m times b minus a. Altogether, what we obtain? Epsilon over b minus a, right? M is cancelled, times sum of delta ti. Now that is precisely b minus a, right? If we add all those delta ti, that is precisely b minus a. so epsilon. So what is it? Oh, I need 2 also. Oh, doesn't matter. Doesn't matter. So look, you see, I minus this sum is less than epsilon, right? And this sum minus integral sum for our integral is less than epsilon as well. If we unify, what we obtain? So for arbitrary epsilon, we found a number which is minimum of delta and delta 1 positive, right? Such that for all partitions P with diameter less than delta, less than this minimum, delta 1, and for arbitrary points tau I in Ti minus 1 Ti, we have difference, model of difference between I and T of F P tau I, yeah, is less than, so less than difference between I and this sum plus difference between sum and this T, right? According to triangle inequality. Each of them less than epsilon, so less than 2 epsilon. And it means that there exists the limit of those integral sums, which is equal to our integral. Theorem is proved completely, right? Theorem is proved completely. Okay. Now let me write down some properties of the integral along a curve. First, the value of the integral does not depend on an admissible parametrization. And second, the integral is additive with respect to curves. Also, the integral is linear with respect to functions. Okay, let us prove those properties. So, the first property So recall what is admissible parameterization. It means that we can substitute, let's say, t equals to t of another variable. Let it be tall. I don't plan to use the definition, so there will be no mixture with tau from integral sums. We will not use integral sums anymore. Where tau varies, let's say, in CD. What means admissible parameterization? Admissible parameterization for a smooth curve is not good. Is differentiable function is a continuously differentiable function such that t prime of tau is not 0 on CD. If it is never 0, then what can we say? And derivative is continuous, and what it means? So if you have a continuous function which is never 0, right, on a closed interval, then it preserves its sign. So it is either positive everywhere or negative everywhere, right? And if derivative is positive, then what can you say about the function? It's increasing, yeah. And in fact, it is strictly increasing if derivative is never 0, right? Yeah. So in particular, it means that for sure admissible parameterization is given by a strictly monotone function. Okay, so then look, what is about our integral? As we know, the integral we have proved the integral equals to from a to b f x of t, y of t, z of t, r prime of t dt, right? Then look, we made a substitution in the integral, right? So let's compute what happens with the right hand side if we make this substitution, right? If we make a substitution, we know how to replace, right? So I should write integral from, let's say, t minus 1 of a up to t minus 1 of b, right? I should change the limits of integration. Then I should substitute x of t of tau, t of tau, y of t of tau, z of t of tau, then r prime of t of tau times t prime of tau d tau. Then look. First of all, according to the chain rule for vector functions, which I used once, so chain rule for vector functions, what it says? Chain rule for vector functions gives the following rule to differentiate. So derivative of this equals to r prime of t of tau times t prime of tau, right? Of course, it's better to, here we have vector that is scalar, so it's better to write scalar before, but I mentioned when I used this chain rule that I prefer traditional order from the point of view of chain rule, not from the point of view of vectors and scalars. Okay, then, look, if I want to compute the length, right, then I should put modulus everywhere, right? Now, look, I don't know about the sign of t prime. It might be positive or negative, right? But, okay, if it is positive, then what happens? What is it? That is c, and here we have d, right? If it is positive. And I may put here modulus without problem, right? Because it's positive. Okay. But what happens if t prime is negative? That means it's decreasing, right? Then here we have what? We have d, right? And that is c. But we know the rule for Riemann integral. We can change limits, right, in inverse order, and put minus. And if we put minus, look, minus t prime is precisely modulus if t prime is negative. So it means in both cases I can write like that. It is integral from t to d f of x of t of tau, y of t of tau, z of t of tau times, now you see, I have modular here, right? And product of those two modulus is precisely that one. So times modular r of t of tau prime d tau. And what is written now? It's precisely what we should write instead of this integral according to our theorem, right? If we use instead of t parameter tau. So what is written here is precisely our curve when we replace parameter t by parameter tau, right? Also replace t by tau. That is vector, right? So it means indeed the value does not depend on the parameterization. That's very important property, of course, right? So it means doesn't matter how you parameterize your curve. The integral is the same. It doesn't depend on parameterization. And of course, physically, it's also doesn't matter how you parameterize your curve. Mass is the same, right? Yeah. Okay. Now additivity property. Additivity property means what? It means, so if we have a curve gamma, and we split it into two curves, gamma 1 and gamma 2, let's say, right? So gamma is gamma 1 together with gamma 2, but not simply just a union, but you see, it's like that. So you have one curve, after that, so the end of gamma 1 is simultaneously the initial point for gamma 2, and you continue, right? And you obtain gamma as a curve which consists of two curves in this order, one by one, right? And in that case, obviously, you see, in fact, even integral sums, they consist of, you may split also integral sums in two parts, right? And this additive property follows easily by this consideration. So additivity means that integral over gamma f ds equals to integral over gamma 1 plus integral over gamma 2. And let me remark also here that this can be considered as a definition of the, no, not a definition, in fact. It can be used, it can be used to extend our theorem. It can be used to extend our theorem to the case of piecewise smooth. So if you have a curve like that, piecewise smooth, right? Then how you can compute? Still the same formula is valid, but how you should prove it? You just split the integral into several parts, right? For each part you have smooth curve, apply the theorem, and then add the results. That is how to extend the theorem. In fact, in that book of Friedman, the theorem was given for piecewise smooth curves. But in fact, the essential part is just for that one. And the last, linearity, is obvious, right? What means linearity? Third, linearity means that integral of alpha f plus beta g ds equals to alpha integral f ds plus beta ds for arbitrary alpha beta real. That is linearity. And that is obvious, right? Because you see, all integral sums are linear with respect to functions, right? So you don't need to prove anything here. Okay, I think that's all for this section, and that's all for today. I don't want to start new section. Thanks for your attention.